His talk is entitled Characterizing Land Cover and Vegetation Dynamics Using Earth Observation Systems. So without further ado, Dr. Khatami, the floor is yours.
Thank you so much, Dr. Karimzadeh. Hello, everyone, and thank you for having me. So at the LUECI Institute at the University of Florida, we are interested in applications of remote sensing for mapping and quantification of environmental change. Today, I'm going to present 2 sample projects from our work, and I'm going to mostly focus on methods and techniques we use in these projects. So the first project is quantification of recent land cover change in Ethiopia. So Ethiopia has been a hotspot of agricultural land acquisition or land transactions over the last few 10-15 years. Ethiopia has high levels of food insecurity and high levels of poverty, and the government of Ethiopia aims to be a lower middle income country by 2025. Given that the majority of population, about 85% of the population, relies on agriculture for livelihood, agricultural sector has been the major source of growth for the country. But what are the land transactions? Land transactions are simply the practice of converting smallholder farms into intensive large industrial farms. In many cases, especially in Ethiopia, these large farms are rented to foreign countries for agricultural production. Here you can see an example of a transaction site. You can see the high resolution images for transactions before and after transactions happened. So there has been many discussions about the advantages and disadvantages of land transactions. On one hand, transactions can lead to deployment of new agricultural techniques that can lead to increase in crop yield and eventually lead to economic growth. On the other hand, there has been many publications that show that increase in yield has been very limited, but the transaction has caused displacement of households, losses in household income, and losses in and dissatisfaction of farmers. So our overall goal in this research is to examine the effects of land transactions on agriculture, ecosystem services, food and energy security. And as part of this big project, we have created land cover maps for two time periods: 2006 before the transactions and 2017 at 30-meter spatial resolution. And today I'm going to present our land cover maps. So our classification is based on a classification scheme with 6 broad classes, including dense forest, woody savanna, cultivated bare soil, and urban and water class. So we use Landsat for the 2017 classification. We used Landsat 8 as the main source of remote sensing data. We use data from March 2016 to March 2018, about 3,000 Landsat images for classification, and here you can see the footprints of 65 Landsat scenes that cover the whole country. Because images were collected at different dates, we needed to create image composites that we could use in our classification algorithms. So we created 3 different image composites. The first one was probability density function, or PDF composites, for which for each pixel we took the whole time series of observations and we extracted 5 different percentile of values for each pixel per each band. The second composite was seasonal sequential composite, in which we divided the entire data to 4 different seasons. And for each season, we calculate the median value per pixel per band. For the third composite, we used a sinusoidal model to fit it to the NDVI time series of each pixel. So we took the NDVI time series of each pixel and fitted a model with 4 terms, including a constant, a linear term, a sine term, and a cosine term. And after fitting the model for each pixel, we used the 4 coefficients of the model as additional exponential variable for the classifications. In addition to the Landsat data, we used MODIS data and created the similar composites. And because for the MODIS, we had higher temporal resolution, we created, for the PDF composite, we extracted 10 different percentile, and for the sequential composite, we created monthly layers. Here you can see a visualization of our composites. At the top right, you can see an area mostly covered with a high resolution of an area, which is mostly covered by forest, cultivated, and urban classes. On the top right, you can see the visualization of the Landsat NDVI sinusoidal model. The RGB bands here correspond to the coefficient for the cosine, sine, and linear term. As you can see, the composite can separate the target classes very well. Another example is the Landsat PDF composite. Here, the visualization is based on 95%, 75%, and 50% of NDVI values. Again, the target classes are very separate. And for example, urban areas appear as black because NDVI for urban class is low. And for the forest class, it appears very bright because forest class has high NDVI for most of the year. In addition to the composite, we extracted textural layers based on different window sizes to capture textural information at different scales. We used the panchromatic band from Landsat at 50-meter pixel size. We also used elevation data from SRTM. We extracted the slope and aspect. And we also used the nighttime light data to improve classification of urban areas. In terms of reference data, we collected 300 to 400 reference pixels for each class based on a stratified random sampling. And for stratification, we used two existing land cover products, including Copernicus Global Land Operation and Global Land 30 to do the spatial stratification. After that, we write a code to highlight the footprint of each reference pixel on Google Search Engine, and we manually collected the reference labels for each of the reference data. Finally, we divided the reference data to 70% for classification and 30% for accuracy assessment, and we used a random forest classifier to create land cover maps. We repeated the same process for 2006, created similar composite, collected reference data, created the land cover maps. Here you can see the final classification products, and the most obvious trend here is the increase in agricultural lands in the center and the north part of the country. After you do the classification, the next step is accuracy assessment and estimation of the area of land cover classes and area of change. These are statistical estimation questions. In a statistical estimation, we have a population that could be any collection of objects or individuals about which we want to make an inference. For our case, the population is the total number of total pixels in the map. We usually want to know a parameter or summary measure that describes the population. For example, we want to know the average income of people in US, or the proportion of graduate students at CU Boulder, or the total area of land cover classes. If we don't have the response variable for the whole population, which is the case in most cases, we need to take a sample, calculate a statistic, which estimates the parameter. But what can be confusing is that the equation for the parameter and the statistic could be very different. For example, let's say we want to know the average age of all the CU Boulder students. So the parameter is the simple average of the age of all the students in CU Boulder. Now let's say we know that 90% of the students are undergraduate and 10% are graduate students. If we take a sample of 50 undergraduate students and 50 undergraduate students and 50 graduate students, the question is, can we simply average these 100 individuals, the age of 100 individuals, to get an estimate of all students? I think it's very clear that we cannot do that because we have equal number of samples from the two groups, but we know that graduate students only represent 10% of population. So the equation for the statistic in this case is based on a weighted average of observations. So the equation for the statistic would be different from the parameter. This might seem very clear and intuitive for this example, but when it comes to accuracy assessment, map accuracy assessment, you can find many papers that have used wrong equations and wrong formulas for accuracy assessment. So in map accuracy assessment, the goal is to estimate a population error matrix that shows the number of correctly and incorrectly classified pixels for each class. Here you can see the population error matrix in terms of pixel numbers. We can also define error matrix in terms of proportion of area by dividing the number of pixels in each cell by total number of pixels in the map. We can define some summary measures such as overall accuracy, user accuracy, and producer accuracy. In practice, we don't have the full coverage of reference data, and again, we need to collect the sample data to estimate population error matrix. But similar to the example for estimating mean age of students in CU Boulder, here, depending on the sampling design, the equation for estimating population error matrix could be different. For example, if we take a stratified random sample with map classes as a strata, we need to account for the different proportion of classes in the map. Or if we have taken a sample, have done a cluster sampling and sampled cluster of pixels, we cannot treat the sample as simple random sample, and we need to account for the spatial correlation of the samples within each cluster. Because we use a stratified random sampling in this research, I'm going to focus on estimators for stratified random sampling here. So let's say we have collected a sample of reference data and formed a sample error matrix. Now we want to estimate population error matrix. So we have the table on the left and we want to estimate the table on the right. If we had a simple random sample, that would be easy. We simply could divide every cell in the table by the total number of samples, and we would get the corresponding proportion in the population error matrix. But if we have done a stratified random sampling, and here we assume that the stratification is based on map classes. So we use map classes as a strata, and for each map class, we take a sample. If we have done that, we need to account for the proportion of map classes, and in the estimator, we need to weigh each observation differently. For example, let's say we have in our map, the water class covers 10% of pixels in the map, 10% of the area, and we have taken 50 samples for each class. Let's say from those 50 pixels for water class, 40 of them are true label of water, which means they have classified correctly. So now what is the element P2 and 2, which is the proportion of area of water class, proportion of the map that is classified as water and is classified correctly. So it would be 40 divided by 50, but we need to multiply it by 10% because that's the proportion of water class, and what we get is 0.08. If we use the wrong equation, we use the simple random equation, we would get 40 divided by 200, which is the total number of samples for 4 classes, and we would get 0.2, which is biased and is not twice more than the 0.08. So we use the stratified sampling and stratified estimator to do the map accuracy assessment. The next question is, how can we calculate the area of classes, area of each land cover class and area of change? Note that what the map gives us is the area based on classified labels. But what we are actually interested is the area based on reference labels or the true labels. So there are a few things we can do. We can use the map as estimator of the area. So we can trust what the map says, but all maps has error, and a small error in modeling can translate to large estimation errors of area when we generalize the model to the entire case study. Note that if we use this method and use the map only, it means that we are not using the reference data at all. The second option is to use the reference data for area estimation, because for accuracy assessment, from accuracy assessment, we have a sample of reference data. We can use the same data to estimate the area of each land cover class. If we do that, we are not using the map for area estimation. The problem with this method is that it could sometimes result in high standard error or low precision of estimations. The third option is to use both data sets. So we can use a model-assisted estimators. So model-assisted estimator can be used when we have a sample of response variable of interest, and we also have a covariate, and we have full coverage for that covariate that correlates to our response variable of interest. So we can use that covariate to improve the estimate of the response variable of interest. In our work, we use a model-assisted estimator called difference estimator. We define two binary variables. For y variables, it could have values of 1 and 0 depending on if a pixel has the reference class of interest or not. So for example, if we want to estimate the area of water class, if a pixel has reference or true label of water, the value for y, it would be 0, it would be 1, otherwise it would be 0. For the x variable, it could have values of 1 and 0 depending on if a pixel has the map label of the class of interest or not. Then the error term can be defined as the difference between y and x, or we can say y equals x plus error. So the population total for y would be our parameter of interest, which shows the total area of class of interest based on reference classification. To know Ty, we need to know Tx and Te, which is the total population total for x and population total for error. The Tx is known because we have full coverage for x, and Te can be estimated based on a sample. Because we have the sample from accuracy assessment, we can use the same sample to estimate the total value of error. And because in our research we use a stratified sampling, we use the stratified estimator to estimate total value of E. So finally, we get the results for accuracy assessment and area estimation. The overall accuracy for the two classifications, two maps, were close to 76, 77%. And in terms of area of land cover classes, the large increase in cultivated land was observed. The area increased from about 150,000 square kilometer to almost 230 square kilometer. And the other major changes were increase in dense forest class and a decrease in savanna class. Also note that the difference between the area estimates from the map and adjusted based on classification error. You can see that the map has overestimated area of cultivated land in 2017 and have underestimated area of forest in 2017. So in the next project, we are investigating the global vegetation persistent change across 4 decades. So there has been many publications investigating vegetation change and vegetation trends at global scales. And some of these publications showed that there has been some greening trends, especially in the North Hemisphere over the last few decades. So we asked if these patterns and trends match up over space, and do they hold true across all seasons, or there are changes between different seasons. We also wanted to know if these trends hold for all biomes, or there are winners and losers in these greening trends. So we are not looking at greening per se, because this has been done before using NDVI and other vegetation indices. What we wanted to do is to develop a statistic that would allow us to monitor persistence over time. We specifically were interested in being able to assign statistical significance to our result. So we developed a few persistent metrics, tested them at local scales, and now we have gone global. So what we are doing is analysis of NDVI at pixel level and at the steps of year and season. We developed 3 different persistent metrics, and today I'm going to introduce our directional persistent products, which are directional change in NDVI in each year compared to a baseline period. To calculate directional persistence, we need to first establish baseline NDVI value for each pixel. The baseline value can come from one or several years of observations, and then after establishing the mean NDVI for the baseline, for the subsequent years, the mean annual NDVI is compared with the baseline, and the t variable can have values of +1 or -1 depending on if the observed NDVI for a given year is higher than the baseline or less than the baseline. Then the directional persistence can be calculated as the aggregation of all t values over time. Under the null hypothesis of no change, the t values would follow the Bernoulli distribution, and the directional persistence, which is the aggregation of t values over time, would follow a random walk process, and which would be the distribution value would represent by Pascal triangle, and the Pascal triangle can be used to do a statistical test and identify critical values of a statistical test. So for example, if after the baseline period we have 20 years of observations, any persistent value of larger than +10 or smaller than -10 would be statistically significant at significance level of 0.05. So we implemented the directional persistence using NDVI data from AVHRR, and we use data from 1982 to 1986 as baseline, and data from 1987 to 2010 as change years. We also divided the data to 4 different seasons, as you can see here, and we do the analysis for each season separately for the whole process. So here you can see the results of our persistence. The change count layer shows that for a given pixel, for how many years we have valid observations, and using the change count, we can do a statistical test to see if if the persistent value of a pixel is statistically significant or not. So here are the persistent values for the 4 season. As you can see, persistent values are the positive persistence dominates the most areas, especially for the North Hemisphere for most of the seasons. So we calculated the directional persistence for 4 seasons and did the statistical testing, and now we are presenting the results for different hemispheres, different biomes, and seasons. For the biomes data, we used a biome classification based on the work by Olson, a publication in 2001, which has 14 biome classes globally. For December, January, February season, we had higher positive trends overall, especially for boreal forest and temperate forest and savanna. For tundra and shrubland and grassland, we had more negative persistence. For March, April, and May, the proportion of positive and negative persistence were very close, with slightly higher positive trends for broadleaf forest, desert, and tropical savanna. For June, July, August, we had overwhelmingly higher positive trends for all classes, for all biomes, especially for boreal forest, temperate forest, tundra, broadleaf, and forest, and tropical savanna. A similar trend was observed, and most of the biomes had more positive persistence on September, October, November. So overall, June, July, August, and September, October, November had higher persistent values, and we also observed more positive persistence in North Hemisphere than South Hemisphere. And the biomes, the forest biomes were the biomes that had positive persistence for most of the seasons, and savanna, grassland, and desert had more mixed signal, and they had positive persistence for some seasons and negative persistence for other seasons. In addition to the biomes, we look at the land cover and different latitudes. So we created some charts that show proportion of negative, positive, and negative significant, positive significant, and no significant of pixels of each biome for different seasons and for different ranges of latitude. We also quantified the proportion of land cover within each biome for different ranges of latitude. I'm not going to go through every single biome, but here are the examples for 2 different biomes. So for the tropical moist broadleaf forest biome, you can see that the majority of land cover classes are agriculture and forest, and you can see for all seasons the positive persistent dominates, and there is a stronger positive signal for North Hemisphere than South Hemisphere. For tropical dry broadleaf biome, the majority of land cover is agriculture and grazing. And you can see that for the North Hemisphere, there are more positive persistence, but for the South Hemisphere, there are more negative values, especially for September, October, November, and December, January, February. So overall, our vegetation persistence results match and aligns with the observed global greening trends, and the approach that we develop and the metric we develop can be used to highlight the areas of positive and negative patterns of vegetation persistence over time. And especially we are able to assign significant levels to the vegetation change at pixel level, which is very important for is an important contribution to the study of vegetation system at global scales. With that, I finished my presentation. Thank you so much again for your participation, and I would be glad to answer any questions.
Thank you, Reza. This was a great talk, and I feel like there was so much for me to swallow. I'm gonna ask a couple of questions because there is a 20-second delay with YouTube. Folks, please feel free to post your questions on in the chat box. So, Reza, the map accuracy assessment, and I very quickly took a look at your papers as you were talking. Those seem to be novel in your work, right? In terms of, well, we usually generate a confusion matrix just looking at our validation versus map data. Mm-hmm. Whereas your point was that, well, you need to think about the prior and what the distribution of those classes are in the maps. So am I getting that right, that was actually a novel piece of work?
Yeah, okay. So there has been many work on this topic on map accuracy assessment, and it has been the major focus of my research. And actually, I maybe could show you a few more slides.
Yeah, this is fascinating. And as you're looking for your slides, as I was thinking, is that this is useful to a lot of people, but obviously it takes engineering and a little bit of coding to replicate all of these, and whether there are libraries or you develop libraries to do that kind of assessment. And if not, what is our next best library to use when we are reporting on accuracy? Sorry, go on.
Yeah, sure. So I just want to show another piece of our work. So the estimation of the error matrix is not the end of for accuracy assessment. So in accuracy assessment, what we do is so we estimate a confusion matrix, but confusion matrix and summary measures such as overall accuracy do not provide any information on the distribution of the error. So what we are doing, we are looking at the distribution of error. So we are looking at the methods that we can interpolate the classification accuracy, and in addition to the confusion matrix, we could create maps that represent where are the misclassifications or the probability of misclassifications. So we have a few publications on this topic, and so what the maps we create, if I not sure if I have this slide. So we want to create maps similar to this. So in addition to the map, the land cover map itself, we are creating maps of predicted accuracy at pixel level. So it shows that where are probably the misclassified pixels. These maps can be used to improve the classification by sampling more data from areas with more misclassified pixels, and also can be used when we are using data assimilation or modeling. These accuracy metrics at the pixel level can be used to account for uncertainty in the data and improve modeling process.
Right. That is fascinating. Again, out of selfishness and folks who do remote sensing and evaluation, these formulas are in your paper. They were not terribly difficult to replicate and implement. You know, when we are doing our coding, we just in the confusion matrix and accuracy and user, etc. Are there a little more advanced libraries that we can possibly use to look at these kinds of things?
There are a few works. So, for example, Department of Geography in Boston University, I know that they have been working on a software that facilitate these calculations, so you didn't need to do them manually and write the code. I don't know if the software is public, but I know that they have been working on that.
Right. Great. Yeah. Thank you. I feel like I will add these papers to my quick reading list. We do everything spatial, but then when it comes to assessment, we often forget to look at the spatial distribution. Questions coming in. Behzad Wahidi is asking, thanks very much for an interesting talk. Is the persistent metric generalizable to themes other than vegetation?
Yes, so the persistence that we create is calculated for any land cover. So we are creating it at global scale and for every pixels, for every piece of land. But depending on your analysis and your study, you can mask for different land cover classes. So we have been using this persistence product, and I would be more than happy to share with anyone interested in the data. We have been using the data in different research. So we have used it for study of desertification in the Middle East. We have used it in vegetation loss in Ecuador, and we have used it in South Africa to study the health and changes in national parks. So it can be used as a proxy for vegetation change to quantify change, and depending on the study you can use it for different land cover classes.
Thank you. Another question is, how often do you need to do boots on the ground validation?
Well, it depends. It depends on the. So you mean that how often we need to collect data?
I believe so. I believe this is about much that is in the chat, but I believe the question is about fieldwork kind of validation and in situ observations, be it perhaps radiometric or I don't know, other kinds of visual assessment.
Yeah, so for the, if you're asking about map accuracy assessment, well, it depends. It depends on if there are high resolution data available, high resolution images available or not, or what are the other sources are collecting reference data. Sometimes the field work could be more accurate, but it's not always the case. So for example, if you want to do a classification for 2006, there is no way that you can do field work. Also, even if you do collect the data for the current time, the time for collecting the reference data using fieldwork could be different from the time that the sensor captures the data, so there could be a gap. So it's it's a question of application. It can be different from one application to another one. Sometimes fieldwork is more useful, but it's not always the case. Depends.
Thank you very much, and feel free to follow up in chat if there are still questions or unclear. Uh, I will go ahead. Another question. Oh, they're asking, for instance, in some parks in South Africa, there can be decadal changes.
Yeah, that's true. Actually, we have a study about parks in South Africa. I don't have the slides, but here is one publication that we are using persistence data to study vegetation change within and outside parks in South Africa. And the persistence metric showed that for some seasons, we can see a greening trend inside the parks, but negative persistent values outside the park. So again, the persistence metric can be used it could be for 1 year or several years if there is a greening process or not.
Thank you. And this, again, really great to know that this metric exists globally. I will wait for other folks' questions, but in the meanwhile, as you were presenting in both your scenarios, obviously handcrafted features such as NDVI or incorporating time series of NDVI, if I'm saying this right, and then using them in algorithms such as random forest. What holds us back at this point to not use an end-to-end, let's say, deep learning kind of approach in which we don't have to do perhaps imperfect handcrafted features such as NDVI or its derivatives? Is it computational resources? Is it lack of enough training data or other reasons?
Yeah, so first of all, I want to talk about random forest. I think it's a great classification algorithm. It can handle and prioritize different sets of explanatory variables. So you can just fit in a large number of explanatory variables, and it would select the variables that are more relevant and more useful. And the random forest is very immune for overfitting. So it's a great classification algorithm. But yes, there are some new works on deep learning and showed promising results. But if you see, most of the publications are applied on very small areas because deep learning requires large number of sample data. And also you need to have, for deep learning to be more useful, you would have a lot of contextual information. So some research has shown that deep learning is more useful when you work with very high resolution data. I'm not sure what is the effect of deep learning if it's applied on large pixels at like 30-meter resolution. But as you said, the another limitation is the computational resources required by deep learning. So deep learning has been used, as I said, on very small areas, and I haven't seen any research that used it at national scale or global scale. So having enough reference data and having enough computation resources still the main limitation of deep learning, and these methods are still at the experimental level rather than operational level, operational land cover mapping.
Right, thank you. And yeah, completely understand that deep learning has its limitations, especially when it comes to labeled data for training, as well as computational resources for large-scale processing. This is my last question. So folks, if I don't see questions in chat, I will wrap up after this question. I wanted to get your thoughts about the applicability of the persistence metric in other domains. Where do you see it being useful to different domains or scientists doing different kinds of things? This goes back to the question of whether it's applicable to things beyond vegetation.
Yeah, that's true. So as I said, we have used the same metric, same product for different kind of studies, for deforestation, for burned area, for vegetation health in national parks. But also the methods that we have developed is not just based on NDVI. So the time series analysis and the metric we developed and the statistical testing framework that we developed is not only applied for NDVI. Any kind of metrics can be used. So it could be applied on time series of water index or any other kind of index. As long as you have the time series, you can apply this persistence instead of, in that case, instead of vegetation persistent, you would get persistent for a different kind of material or land cover. So the theory and the statistical testing framework is the same, and it could be applied on any indices that you want, and there is no limitation on that case.
That's great to know. We obviously, I hope folks now know about this metric and that the data is available. You're welcome to email Reza and reach out if you need the data. If I understood correctly, right, Reza? You mentioned this is available.
Yes, I would be more than happy. So we actually have created two different data sets. I presented one of them today. So we have AVHR data from 1982 to 2010, and we have created persistence using MODIS data at higher resolution, 250 meter resolution from 2000 to 2019, the most recent product we have. And I would be more than happy to share it with anyone interested. You can just open them on your case study and see if you can see any signal relevant to your work.
That's great. Thank you for clarifying on the two data sets. Again, you're all welcome to reach out to Dr. Khatami. I would like to thank him for this great talk and sharing all this information. I would like to thank our colleagues and other departments for tuning in. Next week on Friday at noon, we have another geography colloquium by Dr. Elizabeth Tillman, who's currently at Columbia University. She's starting as an assistant professor at University of Arizona this fall. The title of the talk is Understanding Flood Risk from Space, Opportunities to Adapt to Changing Risk with Improved Monitoring and Accessible Insurance. So I invite you to join us next week, Friday at noon. The colloquium calendar is posted online and the links. Thank you again, Dr. Khatami. This was such a great talk. I appreciate you making time for us.
Yeah, sure. Thank you so much again for having me, and have a good weekend, everyone.
Have a good weekend, everyone, and stay safe and well.